Okay, so welcome everyone to our Tuesday seminar. We are happy to have Ramon Van Handel, who is spending the year, right?
Yes, I'm here all year.
All the way from Princeton University.
Yes.
But he promises that it's a completely different institution, and we're really enjoying Ramon's questions and all the seminars. So please do your best to reward Ramon with some questions today. Comments?
So thank you, Irit. Yes, I'm really delighted to be here for the year, and it's totally worth the extra 10 minutes of my commute every day to to have your wonderful company. So I want to tell you about his recent work, primarily with these two really absolutely fantastic young guys, Anthony Chen and Jorge Vargas. I will have to work my way up to what strong convergence is. But let's start a little bit more down to earth. So let's start by thinking about a graph on n vertices that is d-regular. Right, so every vertex has d neighbors. And I'm going to denote by A its adjacency matrix. And so this adjacency matrix has exactly d1s in every row, and the rest are zeros, right? So clearly, if I act this matrix A on the vector of all ones, this is D times the vector of all ones, right? It's obvious, which means by the Perron-Frobenius theorem that the largest eigenvalue of the adjacency matrix is always basic fact. And one of the natural questions you can now ask is if the largest eigenvalue of this adjacency matrix in the irregular graph is always D, how small can we make the second largest eigen? It's a very old question, and it's of great importance in many different areas, because, for example, this question can be reformulated as on which d-regular graphs do random walks mix the fastest, right? And this leads us to the notion of optimal expanders, and this is something of huge importance in many different areas of mathematics, experimental computer science, and other. So it's a basic question, and the answer was given many years ago in the 1980s by Alon Van Handel. It says that for any d-regular graph on n vertices, the second largest eigenvalue is at least 2 square root d minus 1 minus little l1. So little l1 is as the number of vertices goes to infinity with the degree being fixed. There's a kind of speed limit on how fast a random walk on a graph can converge to equilibrium. Right? It cannot happen too fast. There's a speed limit given by this lower bound of the second eigen. So once you have such a lower bound, I'll come back to what it means. Once you have such a lower bound, then you naturally ask the question, well, can we get graphs that actually achieve this kind of lower bound, that have second eigenvalue 2 square root d minus 1, or roughly 2 square root d minus 1. And there were, in the 1980s, absolutely beautiful deterministic constructions of Ramanujan graphs by Lubotsky, Philip Sarnak, by Margulis. I mean, we probably most of you have probably heard of these constructions. But these are very special kind of graphs, right, that were very carefully constructed using group theory and number theoretic ideas. And, you know, a natural question you might ask yourself is how prevalent is this phenomenon, right? So, for example, if I draw a random d-regular, I just pick one at random. Is it true that its second largest eigenvalue is approximately 2 square root d minus 1? And it was, my understanding was it was conjectured by no God known that the answer was yes in the 1980s, and it took a long time to prove it, but it is in fact true, and this is a very famous theorem of Friedman.
We'll be here in a couple of weeks to give lectures on some related stuff.
Yes.
John Friedman.
Yes, Joe Friedman. So I advertise his talks. I don't know what he's speaking about. But Joe Friedman says that if I draw a random d-regular graph, we have that the second largest eigenvalue of the adjacency matrix is upper bounded by 2 square root d minus 1 plus little as the number of vertices goes to infinity with the degree fixed in probability. So This is Friedman's famous theorem. And this was not an easy theorem. It was a really difficult theorem. The proof is a huge tour de force, okay? And I think it's fair to say that not many people understand Friedman's paper. I'm certainly not one of them, okay? So, but it was a hugely important breakthrough, but it was a very, very difficult theorem. And when you have a very difficult theorem, it makes it very difficult to push further and extend it into new situations.
So,
About new insights, yes.
the little of one, what is it little o in?
In the number of vertices.
Okay.
Yes, and this is in probability result.
Okay.
So, okay, yeah. The same is true here, the little o of one here, which maybe you can't see from where you're sitting.
Right.
It's also with the number of vertices goes to infinity with the degree. So for a long time, this was kind of the state of the art. But in the last, let's say, 5 years, there have been many very exciting developments that have kind of flown from this from this result. And for example, 2 weeks ago here, there were 2 beautiful lectures by Nalini Ananthraman about a version of this result for random surfaces. Many other developments I'm going to talk about later in this talk. Okay, so in the last 5 years, there have been many exciting developments, refinements of these kind of results, new ideas that have entered this area, and I want to describe to you some of them.
So Ramon, one more conjecture. So could it be that the upper bound is just 2 square root d minus 1 without the plus little of 1?
So Ramanujan graphs, which are very carefully constructed to have this property. In the case of random graphs, there are some conjectures that this happens with a probability not going to 0. Yes. But these conjectures have not been proved. That being said, I've never entirely understood why this question is so important. The precise significance of the constant, why little, the lower bound is minus little o1. So why the upper bound with a 0 here is so important? There are some motivations coming from number theory. There is a zeta function for graphs, which it's satisfying kind of equivalent to having this inequality with a 0. But I'm not actually aware of many applications where this is important. Maybe somebody else can like.
It could be negative, right?
It could be negative, for example, too. Yes, and probably is. It's conjecture to be negative with positive probability. So, but we're not close to answering these type of questions. Are there any more questions?
Actually,
Yes.
I ask something. Maybe you're already going to go over how Alon Gopana works. So just as a reminder, like if you just do the trace method, like which is what I remember Alon Gopana doing, what do you get?
So there are different proofs of Alon Gopana.
Okay.
Some of them use the trace method. Some of them use test functions. I will briefly come back to this, but it's a very elementary argument. For the purpose of this talk, the important question is, what is this 2 square root d minus 1? Where is it coming from? I will mention it, but it will take me, 3 extra minutes to prove Alon Gopana, which I don't want to do. I have other things to do. But I will mention it in just a moment. In fact, I'll mention it right now. So I want to explain how we go beyond this result. And in order to do that, I need to kind of deconstruct. So I offer you a kind of deconstruction of what Friedman actually said, because this is, okay, it's some number here, right? There's some random regular graph, but let's kind of try to reformulate this in a way that will turn out to be more natural, though it's not obvious. So there's kind of 2 questions that we need to answer. The first one is, what does it mean a random deregular graph? Turns out not to be an entirely obvious question, because there are different models of random deregular graphs that are all equally natural in certain ways. And it turns out that most of these models are kind of equivalent. There are contiguity arguments that say if you prove something for one model, it also holds for the other models. I'm going to work with a particularly convenient model, which was also used by Friedman, called the permutation model of random regular graphs. There are other models too. The techniques I'm going to talk about work for most of these models, but I'm going to pick one that is particularly useful for what will come next. The other question we have to answer is, what is this 2 square root d minus 1? What's this mysterious number, right? And the answer is that this mysterious number over here, right, is the spectral radius of the infinite deregular tree. And one of the proofs of Alon that you were referring to is you use the trace method. So you try to count the number of closed walks. And basically it's the realization, right? So you have a deregular graph and you have a deregular infinite tree. And there are basically less closed walks in a deregular infinite tree than are in a deregular graph, because you cannot have non-trivial cycles in the tree, right? And that's basically the argument that gives the lower bound in the loop. So somehow or other, what Friedman has to establish is that these random regular graphs really behave like deregular trees in the limit as the number of vertices goes to infinity from the perspective of spectral theory, which is not an obvious thing.
So I guess along those lines, what are the eigenvalues of the deregular graph? Like, kind of, I mean, I don't expect.
Deregular graph or a deregular tree?
I guess deregular tree or.
The deregular tree is
Like beyond the second one.
The deregular tree is an infinite graph, and its adjacency operator, which we're going to see in a moment, has a continuous spectrum. It's just a closed interval minus 2 square root d minus 1 to 2 square root d minus 1. So every point in that interval is in the spectrum of that operator. This is a infinite dimensional operator. These are matrices, so they have a finite number of eigenvalues, but there are many deregular graphs, so we don't really. That's part of what one has to. Okay, so.
As in, like, should you expect that there's two of them that are close to, like, should you expect that there's like a growing number of them close to 2 root d minus 1?
Oh, no, I not only do I expect that, that's in fact much easier to prove than proving Friedman's theorem. So the empirical distribution of the eigenvalues converges to something called the Keston-McKay distribution, which is the empirical distribution of the infinite dimensional operator properly, if you make proper sense of what that means. And that's a much easier result than understanding the largest eigen. So we know this is true. There's a continuous spectrum and there's a kind of explicit density for the eigenvalues which you can write. I don't know it off the top of my head. So this we know. Are there any more questions? All right, so let me deconstruct. So I'm going to work with the permutation model. And the permutation model, the one drawback it has is that it requires you to have an even degree. I cannot construct a degree 3 graph using the permutation model. I have to, the smallest one is degree 4. This turns out not to be a big deal. I can modify the model a little bit so I can make odd degree graphs. But for our purposes, this doesn't really work. So we are going to work with the permutation model. So how are we going to do this? So I need to create, let me draw a bunch of vertices. So here, for example, I have 3 vertices. And I'm going to draw a graph of degree 4. So what I'm going to do is I'm going to give each of these vertices 4 stubs. And I'm going to use 2 different colors. For example, I can do this. Right, so each of the vertices has degree 4, but there's no graph yet because they're not hooked up. And I'm going to give them a kind of arbitrary orientation, these edges. Of course, we are not interested in directed graphs. We're interested in undirected graphs, but for the construction, it's convenient to have some directions, and that way we'll get rid of it. You'll see that. So I have here, for example, I'm going to construct now a random 4 regular graph of 3 vertices. How am I going to do it? I somehow have to hook up these edges to each other. So what I'm going to do is for each color, I'm going to pick a random permutation. And I'm just going to hook up these vertices according to the random permutation. So let's do an example. So for example, on this side, let me draw a random permutation. For example, suppose I draw 1, 3, 2. Right, so if the permutation sends 1 to 3, 3 to 2, and 2 to 1, right? So what do I do if it says 1 to 3? Then I take the outgoing edge from 1 and I hook it up to the incoming edge from 3. And it says 3 to 2, so I take the outgoing edge from 3 and I send it to 2. And it sends 2 to 1, so I take the outgoing edge from 2 and I send it to 1. So now I've hooked up these blue edges. And now for the red edges, I also pick a permutation. For example, maybe I pick this permutation, right, which switches 1 and 2 and leaves 3 alone. Right? So what happens? I send 1 to 2, so I hook up the outgoing edge from 1 to the incoming edge of 2. It sends 2 to 1, so I go like this. And it sends 3 to 3, so I hook up the outgoing edge from 3 to the incoming edge of 3. Now I've created here a 4 regular graph on 3 vertices. But of course, for the blue edges, I can pick a different permutation, and for the red edges, I can pick a different permutation. I get a different graph. And the permutation model of random deregular or 2D regular graph works precisely by picking uniformly at random these two permutations. If I had a 6 regular graph, I need 3 permutations, etc. Does that make sense? So what I've described here is a directed graph. So what is the adjacency matrix of this graph? So if I pick, for example, suppose this permutation, let P1 be the permutation matrix associated with this permutation, and P2, let me call them S. I usually call them S. S for symmetric group. N stands for the number of vertices. So in this case, I have 3 vertices. So if S1n is the matrix corresponding to this permutation, S2n is the matrix corresponding to this permutation, then what's the adjacency matrix of this graph? Well, the adjacency matrix of the directed graph is just S1 plus S2, right? Just by construction. But I want it to be undirected, so I just add their adjoints, right? And that removes the direction. So the adjacency matrix of this graph is S1n plus S1n adjoint plus S2n plus S2n adjoint. And S1 and S2 are 2 IID random permutation matrices. N vertices here, N is. Does it make sense? There's a very convenient way of defining random regular graphs because you can construct them out of random permutation. But yes.
So how do you deal with the self loop on the third?
So I don't care about these self loops. So in this model of random permutations, the graphs are not necessarily simple. So they can have self loops, and we will see later they play an important role. They can have multiple edges. If you really cared about having a simple graph, you could condition this model on being simple. It turns out that it's simple basically with constant probability. So if you want to say something about simple graphs, then you can just deduce it by condition. So it doesn't really turn out to matter that the model has self loops and multiple edges. That being said, some of the more sophisticated things we're going to show later do depend on the model of the random regular graph, and we will see that. Are there any more questions? So this is on the random regular graph side. And now what I claimed was that this 2 square root d minus 1, this is the spectral radius of the infinite d regular tree. So what I now want to do is I want to draw a completely parallel picture to this one over here for the infinite d regular tree. Well, that's not a big deal, right? So we can start, for example, here with a vertex of the infinite d regular tree. And I will draw 2 blue edges, 2 red edges, give them an orientation. And now, this vertex already has an incoming blue arrow, right? So I give it one outgoing blue arrow, and I give it an incoming and an outgoing red arrow, right? And similar for this vertex. So this one has an incoming red arrow. So I give it an outgoing red arrow, an incoming blue arrow, and an outgoing blue arrow. Similarly here, right? This one has an outgoing red arrow, so I give it incoming red arrow, incoming outgoing blue arrow. Okay, and we go on like this. And now this is an infinite tree, so I get more and more and more vertices. But just like in this model, right, every vertex has an ingoing and an outgoing red arrow, and an ingoing and outgoing blue arrow. If I wanted a higher degree, I just introduce more colors. Does it make sense? So this object over here is basically the universal cover of this object over here that I gave here, including the orientations in the code. So this goes on. I mean, let me try to. Doesn't end here. It's an infinite tree. So far, so good. And what's the adjacency matrix of this tree? So this is an infinite matrix. So this is an n by n matrix. This is an infinite dimensional matrix, right? There's an infinite number of vertices, so it's an infinite dimensional matrix. And the point here is that just like, for example, this S1n is just the adjacency matrix of the directed graph caused by the blue arrows, I can take here some infinite dimensional object, which is S1, which I will call little s1, which is the adjacency matrix of the directed graph generated by all the blue arrows. Does that make sense? And I can take little s2 to be the adjacency matrix generated by all the red arrows. And then the adjacency matrix of the infinite graph is this object over here. And I've just defined these s's in words. Okay? But I hope it's clear from the picture what they are. Does that make sense? Everybody's happy? But just a remark, I'm trying to stay elementary, but these constructions I'm doing over here are extremely natural group theoretic constructions. So if you think of this as the infinite tree, right? So the D regular tree, the 2D regular tree, is the Cayley graph of the free group on D or G generators. Free group of D generators, you can think of the 2D regular tree as the Cayley graph of the free group of D generators, with the generating set being the free generators and their inverse, right? So they're 2D generators. And these arrows that I'm giving here are just which, right? So the blue and red are, so for example, here I have 2 generators, right? The blue and red correspond to which generator, and the direction of the arrow corresponds whether I multiply with the generator or with its inverse. So this is a very natural construction. And if you have this construction, then these SI is nothing else than the regular representation of GI, where GI are the free generators. So there's a very natural way of viewing this in the context of free groups, and this plays an important role in many arguments. But you don't really need to understand this in order to understand. Is it good? Everybody's happy. All right. So now that I've deconstructed the statement, what does Friedman say? Let me rewrite Friedman. Now, there's a further subtlety here, which is that Friedman says something about the second largest eigenvalue of finite graph. But I said that 2 square root d minus 1 is the largest eigenvalue of the tree. It's the spectral radius of the tree. The reason for this is a little bit minor. You see, a d-regular graph always has an eigenvector which has all ones. This is the first eigenvalue, it has eigenvalue d. But if you have an infinite graph, the vector of all ones is not square integrable, right? So this Frobenius eigenvalue simply doesn't exist, right? So it doesn't appear, right? So the second, this largest eigenvalue over here doesn't exist for the infinite dimensional graph, which is why we're talking about the largest eigenvalue of that one and the second largest one of that. There's a more natural way to view this, which is what I should simply do is I should simply take the adjacency matrix, but remove the top eigenvector, the all ones vector. And then I just talk about the largest eigenvalue. So if I now want to rewrite Friedman, I should do it as follows. I should say that the largest eigenvalue of this sum of independent random permutations but restricted to the space orthogonal to the Frobenius eigenvalue, right? So that's really the second largest eigenvalue of the matrix without this. Converges as n goes to infinity to the largest eigenvalue of this infinite dimensional matrix. It's the same statement as Friedman. Well, for d equals 4, right? If you want a d equals 6, you just add a third permutation. Here you got a third generator. That's it. Does that make sense? Good. So what we really think, we should really think of Friedman's theorem as saying that the sum of random permutations is modeled in the limit spectrally by a sum of the generators of the free. Now, once you phrase it like this, you start wondering what's so special about the sum. I took a sum of random permutation matrices, but you know, why just the sum, right? If we really think that these random permutation matrices behave in the limit, like these infinite dimensional operators, I should be able to do better than this. And that is true. And that was a huge breakthrough. This is a vast generalization of Friedman. Which is called the strong convergence of random permutation. And what the strong convergence of random permutation says is that actually, this statement still holds if you replace the sum by any non-commutative polynomial of these random permutations. It says that for any non-commutative polynomial in R non-commuting variables and their adjoints. The norm of P of S1n adjoint SRn adjoint converges as n goes to infinity, the norm of the same polynomial of these infinite dimensional operators.
But if the norm on the left, you still have to.
Oh,
yeah.
I'm very sorry. Of course, I have to remove the trivial eigenvalue. Absolutely, thank you. Otherwise, it's not true. So exactly the same statement. So if I take the trivial polynomial P of S1, S2 as S1 plus S2 plus the adjoints, then I recover Friedman.
But P need not be self-adjoint.
P need not be self-adjoint, but in fact, that turns out to be you see, the norm of X equals the square root of the norm of X transpose, which is self-adjoint. So in fact, without loss of generality, we can work with self-adjoint. But indeed, P doesn't need to be self, but it's not big. And here I wrote norm, there I wrote largest eigenvalue. That's also not a big deal, because if I add a large enough constant times the identity to this polynomial, I just get another polynomial, and then the norm just becomes the largest eigen. That's also more or less the statement. Is the statement clear?
Sorry, so in the non-self-adjoint case, what do we need by the norm? Is the spectral radius still there?
Yeah, just the operator norm. These are operators on Hilbert spaces, and you just take their operator norm. Yes. So if they're self-adjoint, that corresponds to the largest eigenvalue. Otherwise, it's the largest singular value. Let's say. Okay. So this is really a vast generalization of Friedman's theorem. But if you see this for the first time, it may not be obvious why you should care, or what good is this? What Friedman is about random graphs. We kind of understand why random graphs are interesting. Why these polynomials are interesting may not be so clear. But at the basic level, the importance of this result is that polynomials are extremely expressive, right? So you can express many different models, and you can encode many different models in terms of polynomials of random matrices. A random graph is what it is, it's just one model. But it turns out there are many interesting problems surrounding Friedman's theorem, many variants of Friedman's theorem in other situations, in other areas of mathematics, that at the end of the day can be cleverly encoded by choosing polynomials of these random matrices. So this is a hugely expressive result, and it can be used as an ingredient to prove many other things, of which I'm going to give some examples. Yes, Sid?
Is it generalized to other groups and generators?
So these are, so I'm going to talk more about that. But, the answer between this is between yes, we know, and major open problems in this area, right? To what degree this extends to other situations is one of the big questions. Well, we know some of those things, and I'm going to explain at least one example. Not to other groups, but to other use. But for example, the question whether such a result holds for surface groups is a kind of a big question, which so you replace the free group by it. So just to give you an appreciation for how much more general this result is as compared to that result, I'm just going to list for you 4 examples of recent breakthroughs that have used this result as input to prove important things. Okay. I'm not going to explain them really, you can ask me later. Some of them I don't really understand. Okay. Original example, which was already in the paper of Bordenave and Collins, was one of their motivations. Is optimal spectral graph of random lifts of any graph. We start with a finite graph. And then there is a way to generate a sequence of finite covering graphs of the original graph called k-lifts. You basically, what you do is you take your fixed graph, you duplicate it k times, and then you scramble the edges of the graphs between the different copies, right? this scrambling is done by means of these random permutations. Okay, so that's where the random permutations comes in. And now you want to understand whether these kind of much more general constructions than random regular graphs have optimal spectral properties. And the adjacency matrix of these graphs, if you do it properly, they can be encoded in terms of such polynomials of random permutation matrices, and then you get the result boom from Bordenave. Okay, so this is a application to random graphs. Second example was a very large breakthrough of Ackley and Hyde, who asked the same question. They solved a very old conjecture due to Boozer. Which is a similar question to this, but rather than talking about graphs, we talk about hyperbolic surfaces. So it's about the optimal spectral graphs of random covering spaces of hyperbolic surfaces. So now we are outside the discrete world, we're talking about surfaces. So you take a Riemann surface, and then they have a kind of construction that tries to mirror this statement about k lit. You take a surface, hyperbolic surface, you duplicate it k times, and then you have a way of gluing them together randomly. That's like randomly scrambling the edges. And now one is interested in Laplacian. This is an infinite dimensional object, but there is a way. That's the one of the main ingredients of this breakthrough was that they found how to encode the spectral property of Laplacian in terms of this strong convergence. And then again, the result follows. This settled a very old problem in hyperbolic geometry. There's another question which I will just mention very briefly, also in geometry. Was actually last week, Antoine Song gave a beautiful talk at the university, which has nothing to do with spectral gaps. It's about the construction of random minimal surfaces in spheres. So there is a whole conjecture of STL that asks whether it's possible to construct minimal surfaces in spheres that have negative curvature. And he didn't quite solve that, but by what he does is he uses random permutations to enforce some kind of symmetries of his minimal surfaces. Then using strong convergence, he's able to show that these random minimal surfaces almost have a constant negative curvature. They have it on average, they're very close to having constant negative curvature, which is much closer than was accessible before. And one of the funny things about these applications is that usually we talk about spectral gaps. So this is something about norms, so it's something spectral, but there doesn't seem to be anything spectral here. But he's still able to encode it in polynomials, which is to me was an unexpected story. I want to mention something also that is kind of tangential, but that given the history of the subject, I think is important to mention. But this notion of strong convergence doesn't necessarily have anything to do with random permutations. One can use all sorts of different random matrices here and try to understand whether arbitrary polynomials converge in norm to some limiting object. And for example, if you take classical random matrices like GUE, Gaussian random matrices, limiting objects are not the same. They're called free semicircular variables. And the analog of this strong convergence result was a huge breakthrough of Hagerup and Torbjornsson in 2005. And the motivation for these results is in the theory of operator algebras. So yet another area of mathematics. So being able to approximate some non-trivial operator algebra by matrices in this very strong way puts a huge constraints on the structure of these operator algebras and enables one to study structural questions about operator algebras. So this was the original motivation. I'll just write some names. So of Hagerup Torbjornsson. And just in the last year or two, there was a lot of excitement in this area because there were other kind of important problems in the theory of operator algebras that were solved by proving refinements of these kind of strong convergence phenomena, things that went beyond what Hargreaves and Grunstein originally did. So I'll just write the name. So there was an old conjecture called the Peterson-Dom conjecture in the theory of one-normal algebras, and it was there was a wonderful insight due to Ben Hayes that this conjecture, which is just a statement about the structure of algebras, and something to do with amenable subalgebras, can be deduced from some form of strong convergence, not of permutation matrices like I wrote there, but of some other kind of model. And it required new insights into the theory of strong convergence to settle these kind of. So yes.
Specifically, do we know strong convergence if you replace permutation by unitary?
Yes. So in fact, we know much more now, but that's very recent. But we know if you replace them by higher unitaries, we know if you replace them by other classical groups, we know if you replace them by Gaussian models. These are, and we know if we are other situations as well where we use. But new technology had to be developed at every step to handle this. Are there any questions? So, very good. So I'm just trying to explain that the power of this phenomenon of strong convergence, which goes beyond what I wrote here, but it turns out this result is one of the most delicate ones for very good reasons that will maybe become clear later. And in particular, for all but the last application over there, the fact that these are permutation matrices, so some discrete object, was extremely important for the solution of this. Okay, so it turns out to be much harder, for example, than our unitaries. They're much easier. Much easier models. Okay, so now that we have gone through the motivation, let's talk a little bit about proofs. Well, I told you already that Friedman's result is very difficult. And you can imagine that something vastly more general than Friedman's result ought also to be very difficult, right? Because it's much more powerful. And in fact, there were some aspects of Friedman's proof that were previously simplified by Bordenave. He used a kind of morally similar approach to Friedman, but was able to shortcut some of the most difficult parts of Friedman's argument. And the result of Bordenave Collins builds upon that to prove this much more general result. But at the end of the day, the proofs of these results they require hard analysis. Okay? So they require very delicate combinatorial analysis of these random matrix models. And there's a very good reason why these proofs are difficult. And I'm going to explain part of that in the second half of the talk today. But at some level, this is expected to be difficult, right? It really requires a kind of hard combinatorial analysis of what these random permutations do when you take very large degree polynomials. So the work I talk about today came kind of as a surprise. It was not something we were expecting. But it turns out that we have a new approach to proving such things.
So Bordenave Collins, did they use the trace method?
They use some very sophisticated version of the trace. But it's not, there's reasons why the trace method cannot be applied well in this situation. And again, I'm going to try to come back. So we have a new approach to strong convergence. And one of the surprising aspects of it is that it doesn't actually use hard analysis. It's based on soft argument. We never have to do any difficult combinatorics or anything like this. It's just based on almost entirely on soft argument. And, given the kind of history of these problems, it was kind of unexpected that that's even possible, right? That to have a soft argument. And once you have a method that's based on soft arguments, it allows us to do two things. First of all, it enables us to prove of strong convergence in new situations. If you have a soft method, it's much easier to apply it. So you can take much more complicated models and try to apply these methods and see what comes out. Yes,
What do you mean by soft in this context?
well, you will see. The soft means we don't really have to do any combinatorics. It's a kind of miraculous, but you know, I will try to explain by the end of the talk, at least the basic reason. So first of all, it makes it possible to prove things in new situations because it's you know it's easier to apply. But kind of surprisingly, it provides stronger quantitative information. Than previous methods. We're able to see quantitative phenomena of strong convergence that were out of reach of these previous methods. And this is perhaps more surprising even than that, because you know, usually if you have some kind of soft argument, it's very crude, right? So you don't expect to get very detailed information out of a soft argument. You know, usually if you want very detailed information, you have to work very hard. But there's a kind of reason. It seems there's a kind of genuinely new mathematical phenomenon that's not captured by the previous method that we're able to capture using the soft argument that is allowing us to prove stronger results. And this is again something I'm going to try to explain.
So the stronger confirmation means large deviations here?
So let me give you some examples. In fact, it turns out we can get many strong quantitative things out of this in different directions. Things that were very difficult or maybe even impossible by combinatorial means. And there's a reason that I will try to explain later on the reason why what we seem to genuinely be capturing some mathematical phenomenon that wasn't being captured by the combinatorial. I'll try to explain that. So before I go there and to start talking about the method and how it works, I just, you know, I should write down some results. So I'm just going to give you some kind of examples of things we can prove. Okay. So these are just samples. We now have many applications. There's one paper that's on the archive. It's one paper that should be forthcoming in the next few weeks. We have many applications of this method. So I'm just going to give you some kind of nice examples that I can draw pictures of, just to illustrate what's going on. So the first one is even about Friedman's theorem itself. Okay. So let's go back, forget about all these polynomials, all this stuff. Let's just go back to Friedman's theorem itself. Even there, we can say new things that I'm not aware of how to prove it. Let me write down this thing. So let's take a random 2D regular graph in the permutation model that I described before. And what I would now like to understand is what does, right? So we know that lambda 2 of A, right? Lambda 2 of the adjacency matrix converges to 2 square root d minus 1. I would like to understand what the distribution of this random variable actually looks like. So I'm going to try to draw a picture. Here's X. And on this axis will be the probability that lambda 2 of A is greater or equal than X. We're going to draw the distribution of this random variable. So of course, here is 2 square root 2d minus 1, right? Because the degree is 2d. Okay. And beneath this point, basically 1, right? The probability of being greater than something less than 2 square root 2d minus 1 is 1. That's Friedman's theorem, right? The question is what happens when we go above that, right? What are the probabilities of the variable? So it turns out there's a kind of remarkable picture that happens here. So I need some definition. There's going to be an integer. Doesn't really matter what it is for our purposes. There's some number. And we need some other numbers, rho m. The definition. So this is 2m minus 1 plus 2d minus 1 over 2m. And this m star is just the smallest integer such that rho m is greater or equal than 2 square root 2d minus 1. Okay, that's just what it is. So here we have somewhere over here, we have rho m star plus 1. We have rho m star plus 2. Rho m star plus 3, etc. So it goes on like this until eventually we reach D. And we know that the second largest eigenvalue of a random regular graph cannot be larger than its first largest eigenvalue, which is D. 2D, I'm very sorry. So above this point, the probability is just 0, right? So here the probability is 0. So what does it look like? So I'm drawing here on a logarithmic scale. So let me draw 1 over n to the m star, 1 over n to the m star plus 1, 1 over n to the m star plus 2. So, of course, these are decaying exponentially. So I'm drawing this on a logarithmic scale. It turns out that these tail probabilities exhibit a kind of wonderful staircase pattern. Okay, so below here it's 1. Below this point it's 1, so it's coming here from infinity on the scale. And then between 2 squared to d minus 1 and rho m star plus 1, the probability is 1 over n to the m star plus little o. And then as you hit this rho m star plus 1, probability abruptly decays to the next level. When you hit rho m star plus 2, the probability abruptly decays to the next level. You hit rho m star plus 3, the probability abruptly decays to the next level, which is 1 over n to the m star plus 3, etc. Until eventually you hit here 2D and then it ends because the probability of being greater than 2D is 0. But if you're used to seeing what tail probabilities look like of typical random variables of probability, you rarely see this kind of picture. So everything here is on a polynomial scale, not on an exponential scale. You have these very strange abrupt jumps. What is going on here? So actually we understand exactly what is going on here. So if you have these, remember that these random graphs that we're constructing, they can have self-loops. So if you have a self-loop, that gives you a diagonal element of the adjacency matrix. Now you can imagine if you have many self-loops, you will have a very large diagonal element, right? And that will cause you to have an outlier in the spectrum. So it turns out that, so the explanation of this picture is that if the random graph, right, has m greater than m star self-loops on some vertex, then there exists an outlier in the spectrum at rho m. And this happens with probability n to the 1 minus n. Turns out that to show what I wrote here, this is a kind of relatively easy argument, and that gives the lower bound in this picture, because it shows that these outliers give us a lower bound on the tail probabilities. And what our method gives us is an upper bound that matches exactly this lower bound, which means that the tail probability of these second largest eigenvalues random regular graph is completely dominated by the behavior caused by these events. But this is a kind of very sharp understanding, at least at the scale that we hope in these polynomial situations, of the large deviation probabilities of random regular. Yes.
But what if you sample a random irregular graph without self-loops? Like,
Then you have to do another analysis, right? So depending on what model. So you see, unlike Friedman's theorem, which doesn't really depend, like contiguity argument doesn't really depend on the model of random regular graph. The behavior of the large deviations is, of course, dependent on what model you choose. So if you choose a different model, and we can choose different models if we wanted to, we didn't do it, but if you choose different models, then in theory, if you do a whole analysis, you can draw such pictures, and you should be able to understand if you work hard enough what is going on.
And you would expect it still to be controlled by kind of local issues in the graph.
That is very much the understanding that we have of random regular graphs. And that is something that, as you will see, played a huge role in the proofs of these results. For us, it doesn't turn out to play any role in the proof, but if we push hard enough, we are able to actually get a complete picture. So getting such a picture is not something that seems to be accessible by the kind of methods that we do. But for us, if we work hard enough, in fact, we didn't even work that hard here because fortunately, Doron Puder did the work for us. So Doron has this beautiful paper where he does a analysis of the combinatorial group theory of what is going on over here with these random permutations. So he had all of the right estimates that we needed to draw this picture. It just, the estimates are not useful without having a method to connect those estimates, these group theoretic estimates, with the properties of the random graph. So the new approach we have allows us to take this additional information that we have about the model and turn this into a very precise picture of what the second mode should learn. So this is one example of a kind of quantitative phenomenon that is revealed by this method that it was not really accessible before. You good? Sorry, I'm just calibrating my time. Doing very well. So let me give another example. I want to give you a completely different example of a kind of quantitative phenomenon that we can access. That has nothing to do with what I just wrote, but which may be of interest to particularly this audience. So I'm going to show you a kind of models. I'm going to show you new models where we can prove strong convergence. And that go beyond these random permutations. So this was example one, maybe I'll label it. Example one. So one way to think about what I'm going to show you is motivated by the question whether we can de-randomize this notion of strong convergence. There are some papers in the computer science literature that try to de-randomize the Bordenave and Collins result by kind of pseudo-random generations, things like that. This is a computer science point of view. But we're trying to find here natural models of strong convergence that have less randomness, and I will try to explain how this fits into a general. So what did we do here? We drew a number of IID random permutation matrices of size n by n. So we're taking a random permutation of n elements. In order to do that, I need n log n bits. Okay? And then I get an n-dimensional matrix. Does that make sense? Now the question is whether I can draw random permutation matrices with many less random bits and still have such a conversion. So let me give you an example of how, one example, and then I'll put this in the general frame. So one way, right, what I did over there, right? So take the symmetric group Sn. Right? This is a symmetric group on n elements. Draw a random, uniformly at random permutation, right? So I need this is n log n bits. So using n by n bits, I can draw a random element from the symmetric group on n elements. And then I form from this random element this n by n random matrix, right? Snij, which is just defined by its entry is just 1 if I equals sigma j and it's 0 other. So let me write I. The entry of the matrix is 1 if I equals sigma j. This is an n by n. Well, I just think of the symmetric group of n elements acting on the set 1 through n, right? And then I index how it shuffles the elements 1 through n by this adjacency. Now imagine what I'm going to try to do is I'm also going to try to generate an n by n random permutation matrix, but with many less bits. How will we do that? Let's take a much smaller symmetry group, Sm. You should think of this m as being much smaller than n. Right, so now I have only m log n bits. And now what is m? What I'm going to do is I'm going to think, let's form a permutation matrix which acts on subsets of m of size k. So this is n by n matrix. With n being m choose k. So the entries of this matrix are indexed by the subsets of the set 1 through m of size k. So this is about m to the k, which means that the number of bits I'm using is actually n to the 1 over k, which is much smaller than n. Does that make sense? Okay. Now, if I have a permutation of m elements, and I take a subset of k elements, then I can just act that permutation of a subset of k elements. Right? So every subset of k elements gets sent by the permutation sigma to some, right? I just take each element and I permute it by sigma, I get a new element that gives me another subset of k elements, right? So I can just act the permutation on subsets of k elements rather than the original matrix itself. And then I can just take the entries of this matrix, right? So ST to be one if S is sigma T. So the way I've normalized this, you see, is that I have the same dimension n, right? So I have the same dimension n, but I've generated a random permutation matrix using only n to the 1 over k bits. It's much smaller than
How
this.
large can a K be for that?
That's a question. But even if you fix k, let's forget for a moment about how we can grow things. Even if you fix k, it's not clear whether these matrices behave well enough to still get some kind of behavior like this. But it turns out to be true. So you can just plug it in, right? So in fact, these random matrices with much less randomness convert strongly to the same limit as we have over here. So from the point of view of strong convergence, these random permutation matrices, which are generated by many less random bits, still have the same property. That's it gets more and more difficult the less random bits you use.
Ramon?
Yes.
Is the intuition that like this model somehow behaves like a degree k polynomial of the independent permutations to begin with?
No.
I see.
No. I will give you the more general context in a moment. Yes.
Do you have a rate of convergence?
Yes. So I'm going to write it out. So in fact, we have a effective result that allows to grow k with it. And then the question I'll be asked is how fast can we grow k with it? So certainly for k fixed, it's true. And we can even grow k with it. How fast can you grow? Now, our method that we have to prove strong convergence is completely general. It's really specialized to these situations. So the more you know about the group theory of these objects, the better results you will get out. So in our paper, we didn't really spell out how fast you can grow k with n, because it's already, so we use the, I'm not an expert in combinatorial group theory, right? So I use the most basic, simple version of what is going on here in order to prove such a result. But it appears that there are certain forthcoming results in group theory. There was a student, Ewan Cassidy of Michael Maggie, who for his thesis proved some nicer property of the geometric group theory of these objects that should allow you to grow k very rapidly with n. So there's no point for us to spell it out because this is easily going to be obsoleted. So assuming that this conjecture is resolved, in fact, k can be taken as large as a constant times log n over log n, which means that you only need polylog n bits over here in order to get strong convergence. Polylog n is much better than n log.
This gives you a way of sampling Ramanujan graphs with very few random bits.
We don't know for any of these models whether, it's conjectured that
Close to Ramanujan.
close, yes. It gives you a very concrete, nice group theoretic way of generating models that are nearly Ramanujan with very few random.
But we already do know the randomizations like that. But
You know a
it's
kind of
nice.
de-randomization in the computer science sense, but so from my perspective, these are not very natural constructions. What do? You have, it is known that there's beautiful results that say that the Cayley graph on the symmetric group, you can fix some very carefully chosen generators so that this is an expander, not an optimal expander, just an expander. Then you run some kind of Markov chain Monte Carlo using these generators, you get some kind of pseudo-random permutations. Then you work very hard, this was done by O'Donnell and a student. You work very hard to take the proof of Bordenave and Collins and try to check at every step whether it's compatible with this de-randomization. The rates are awful. So that quantitatively the rates are off. Actually, the way they wrote the paper, I can't even tell the paper is strong convergence because there's an order of quantifiers that doesn't make sense. But I've been told that somewhere in the proof, the situation is better than what they actually wrote. But these are not nice mathematical constructions, at least from our perspective, right? These are very concrete group theory construction. I'm going to give you the general context. Okay, so it depends on your perspective, right? I don't know whether one can actually reach constant times log n bits. That's what you would really like if you want to complete the randomization. This I'm not sure of, but there is much about the group theory of these things that we don't understand. So let me just give you the general. This is just an example. I think I like it because it's concrete and it's easy to visualize. But there's a kind of general picture here. Which is that take a compact group. Take any compact group. Of course, before I called G G was a graph, right? Let me call it gamma. Doesn't work. We'll take any compact group. And let's take a unitary representation. So this is a unitary representation of the group. And form, if once you takes a group, a compact group in a representation, you can form random matrices as follows, right? So draw, say, G1 to GR in G according to the Haar measure. According to the Haar measure of the group, right? It's a compact group, so it has a Haar normalized to be a probability measure, right? You just draw R uniformly random generators, and then define your random matrices XIN to just be the representation phi of the ith random element. So this gives you R independent random matrices defined by a representation of a compact group. So for example, in Bordenave and Collins, right, these random permutation matrices with the identity removed, what are those? We just take the group to be the symmetric group Sn, right? And we take the representation to be the defining representation, right? The fundamental representation of the symmetric group. Then you get this model. But all I did over here is I took some other representation of the symmetric group, right? Because I acted the symmetric group on these subsets. They're giving some other representation of the symmetric group that's higher dimensional than the defining representation. And I got a new set of random matrices.
Yeah, but it doesn't work for all representations.
So in fact,
Because K cannot.
so in fact, the theorem I wrote here is nothing special. What we show is that for any stable representation of the symmetric group, these are representations that are consistent for the symmetric group among different dimensions. This is a notion that was defined by Benson, Farb, and blanking on the other people. Any stable representation of the symmetric group, we have such a statement. And this is just an example of such a situation.
I don't understand for which K it's stable.
For any fixed K, it's stable.
Okay.
And if you want to grow K with N, you just need to have a quantitative version of this statement for stable representation, which we have. And then the question is, how good can you get it to be quantitative? But in fact, there's a completely general statement here, which is that for any stable representation of the symmetric group, there's nothing special about these representations. You can have very general representations of the symmetric group, and you can still have these things. And again, I'm not an expert in group theory, but in many cases, it turns out that these constructions give you all representations of dimension up to some point. So I want to advertise, there was a wonderful development by Maggie de La Salle, who, I discussed with, they were here last year as members, and I discussed this with them, our method, and they use their methods to prove something like this. So take gamma to be SUN. And what they showed is that if I take a polynomial, right, of these random matrices defined like this, and the question is, what is the representation? Right? So maybe I should index these by the representation. Let me drop the adjunct, but I mean and the adjunct. you show that you have convergence to zero, right? What I wrote here is strong convergence, but I have to define for you the representation. Of all representation of dimension less or equal e to the n to the 1/24th. Maybe minus epsilon. So we can't quite reach e to the n. If you could reach e to the n, you basically have all of them. Right? Can't quite reach e to the n, that's the same as saying here you can't quite take k to be arbitrarily large. But these are incredibly huge representations of the of SUN. This is much, much larger than was accessible before. See, this is a kind of general phenomenon that when you have random matrices defined by group representations, you can take very high dimensional representations and still have strong convergence. These have much, much less randomness than the original. So again, I'm just trying to give you a flavor of the kind of results you can extract from this. And the key here is to have very strong quantitative estimates that allow you to let the dimensions of these representations become very. Just like here, if you have strong enough quantitative estimates, you can grow k very rapidly. Good. Are there any questions? All right. So I try to introduce what strong convergence is, and I advertise sometimes do various other things. For example, we can handle certain questions that are particularly of interest to operator algebraists about polynomials with matrix coefficients of very, very high dimension. I'm not mentioning it, I'm just mentioning it, but I'm not going to show it. But these kind of questions show up, for example, in the kind of solutions to the Peterson-Tom conjecture. So there are many other things we can do. So for the rest of the talk, I want to give you at least a flavor of kind of one of the core ideas of the method that enables us to achieve these kind of strong quantities. So
for a general group, it's not as obvious what are those SIs are, right? It's something you have to think about.
So when you pick independent random matrices like this, you generally expect to have these being free gen. And then it just depends on whether these still have the individual guys have any relations. For the Gaussian models, these are free semicircular variables. So we often expect when you pick independent random matrices that you get free groups. But it's a very interesting question whether one can get other limiting groups that are different than the free group. And there's some but very limited results in. But if you wanted to do that, you would typically not choose these matrices to be independent. You would typically have to choose them to be dependent because they would have to have some relation.
So whenever you have independence, it's somehow in the limit, it's a tree or something like that.
In the situations we know, yes.
So these S1 of SR don't depend on the representation of this?
No.
No, they're always the free.
You always get the regular representation of limiting group. Again, in the examples that we know. But you know, we know a certain universe of examples, and everything else is conjecture or frontier. So there are many interesting questions. The other interesting questions is that just to give you an open problem, you know, if we go back to Friedman, right? It says that random regular graphs achieve the Lombopana bound. But in fact, we also know Ramanujan graphs, which are deterministic constructions that achieve even better than a Lombopana. Well, they achieve with constant zero. We don't know any deterministic construction of strong convergence, right? So just having a kind of analog of Lubotsky, Philip Sarnak, where you have some deterministic constructions of that achieve strong convergence, it's a really interesting question, and it's not known. Okay? And people have done numerical simulations. I've heard different opinions about what those simulations are saying. And you could ask even other questions that are somehow intermediate. For example, rather than taking SUN, right? So what I did here is I took SUN, I let n go to infinity, and I let the dimensional representation go to infinity much more rapidly, right? But you could also ask, what happens if I take SU2? And I just let the dimensional representations go to infinity. I fix the dimension of the matrix. And here numerical simulations really show that we believe they show that you have strong convergence. Again, currently this is kind of very much in the frontier of what we don't know how to prove this, and there are difficulties, but you know, there's some hope, right? That one can make losses. Yes.
When you say deterministic, it has to be depending on the polynomial. For every polynomial, there'll be some deterministic construction.
No. That would not be strong convergence. You want a fixed construction of a sequence of matrices of increasing dimensions so that for every polynomial you have this.
And you believe it's plausible that you could have less than or equal to for every polynomial? Or it's not obviously false that you could.
It's obviously false that you could have less than, not two, but less than or equal to the norm of this. For every polynomial, for deterministic construction is obviously false. Obviously. Because that would imply by a functional analytic argument that you can embed the C-star algebra generated by these guys into a matrix algebra. That's just not true. However, whether there's an escape hatch is not so clear. You know, maybe it could be that you could have a sequence of matrices such that for every polynomial there's a sufficiently large n, such that you have less or equal to, right? But the n would then depend on the polynomial. I'm not 100% sure whether that also is ruled out by some similar argument or not. There may be some room, but in fact we don't know anything. We don't even know plus little o1. If we're gonna you're gonna ask a much harder question. And just right now there's no deterministic constructions. It's a very interesting question for us. Are there any other questions? So I'm going to try to give you a flavor of what's going on in this method and why it's able to achieve these kind of results. In fact, in the paper, we made a very concrete effort to explain the method in a very general setting, a very clean setting in the second section. So if you know, there's a kind of machine that you can implement that's explained in the paper. So I don't think I will have time to explain every single ingredient of the machine, but rather I want to focus on kind of the main idea that makes it possible to, the kind of new mathematical phenomenon that's going on. So before I do that, I want to explain to you why the trace method, which was mentioned before, has a major problem. And that will kind of motivate what we use. So let's fix a setting. In fact, the method has nothing to do with the permutations or random graphs, so let's fix some kind of general random matrix setting. So we take some random matrices xn, some infinite operator x, say x infinity, if you will, right? And what we want to show is that the norm of xn converges to the norm of this infinite dimensional operator, right? So for example, in the settings we've discussed so far, we may choose xn to be a polynomial of ID random permutation matrices and their adjoints. And we would take x infinity to be the same polynomial as USR. We just fix in the proofs, we fix a polynomial and we work with the polynomial. So we want to show that we converge to infinity. And I will assume, in fact, this assumption is not strictly necessary, but then you have to add a little truncation argument somewhere. I will assume that these random matrices have the property that xn is uniformly bounded with probability 1 by some constant, some large constant k. The constant k much larger than what the limit is. For example, in Friedman's theorem, right, if I have a 2D regular graph, all of the eigenvalues lie between minus 2D and 2D, right, with probability 1. So then k would just be 2D. Right? So we assume we have some bound. It makes our life slightly easier, but it's not true. So this is the basics. And now we have to understand how can we prove such a thing. So if I want to caricature the field of random matrix theory, random matrix theory has, roughly speaking, two main approaches. There's an analytic methods, and there's combinatorial methods. So the analytic methods are typically based on, for example, finding some kind of self-consistent equation satisfied by resolvents. This is a very classical idea in random matrix theory. In order to implement such a method, you need to have a lot of structure. For example, you would need to be able to integrate by parts somewhere. This is not something that you can naturally do with random permutation matrices. I should say that very recently, in fact, I forgot to say it. So maybe this is a good time to take a step back and mention one more thing that I forgot to say. Now, I showed you this picture of this staircase pattern, which shows has a sharp characterization of a large deviation event. Probability theory, there are two very different regimes that require different ideas. One of them is the large deviation regime, which tries to understand the rare events. The other regime is the fluctuation regime, where you try to understand the typical fluctuations around the limiting line. And we are not getting sharp results about the fluctuations, getting sharp results about the large deviation. The fluctuations regime in Friedman's theorem is subject to very long-standing conjectures. It's conjecture that that fluctuations around 2 squared d minus 1 is Tracy with them. And if that were true, then that would answer your question. If the fluctuations around 2 squared d minus 1 is Tracy Wyndham, then you could compute some fixed number, which is the probability the Tracy Wyndham distribution is less than 0, right? Which would give you the probability that you actually get a Ramanujan graph. And very recently, there was a beautiful paper by Wang, McKenzie, and Yao, H.T. Yao, where they made a lot of progress towards this. They are not getting Tracy Wyndham, but they're getting the almost the right scale of the fluctuation, which is the n to the minus 2/3. We are getting a polynomial scale, n to the minus 1/8 or something like this, and we're not getting n to the minus 2. So in some sense, what they are doing is they're taking this analytic approach, but they found a way using switching Markov chains to try to implement this for Friedman's theorem. But their approach is extremely heavily tied to the random graph model. So at least at the moment, it doesn't seem, it's completely unclear that the methods they are using would, they require all the symmetry to generate these kind of integrations. So it's not clear that it would apply to strong convergence. In fact, the rates we are getting, even though they're not optimal for Friedman, actually give the best known rates for strong convergence. N to the minus 1/8 is the best known rate. Bordenave and Collins got log n over log n. So n to the minus 1/8 is for arbitrary polynomials, it's already a major. But in general, in these kind of discrete situations, analytic methods are not powerful, right? Because we don't have analysis. Then we have combinatorial methods, which are usually based on moments. And mostly in discrete situations, these are the main tools we have at our disposal. If you have a discrete model, or you have, for example, a group model, the main thing you can compute are expectations of products of random matrices. This is something you can do. You have tools to compute them. And so these are kind of the main tools that we need to try to compare with. So let me, the rough idea behind the moment method, the classical moment method, the trace method, it's sometimes called, is we want to understand something about the norm of a random matrix, and we don't know how to compute the norm of a random matrix. What we know is how to compute trace. Okay? So what we notice is that if I have an n by n random matrix, this is the largest, let's assume it's self-adjoint for simplicity. This is the largest eigen or the largest absolute value of the eigenvalues of the random matrix. Of course, I can upper bound this by the trace of xn to the power 2p to the 1 over 2p, because what is this? This is just the L2p norm of the eigenvalues, right? The sum of the eigenvalues to the power 2p to the 1 over 2p. Right? It's a sum, so it's larger than the largest one. On the other hand, if I take the sum of these, I can bound their n eigenvalues. So I can bound this by n times the largest one. If I do that, I get n to the 1 over 2p. Elementary bracket is maybe slightly misleading. I have an aversion to brackets. You know, if I just keep adding more and more brackets, then yeah. Here you go. So the point is, if I choose this quantity over here is 1 plus little o1, if p is much, much larger than log n. Basic fact, right? This is e to the power log n over 2p. So the idea of the trace method is that we don't know how to compute the norm. The norm is some kind of very nasty object. We don't have good access, but we can compute these guys with an expectation. Notice I'm putting the brace inside the bracket. That's the big problem, as you will see in a moment. The expectation of the trace of x to the 2p is just a polynomial of the entries of the matrix of degree 2p. All you have to be able to compute is expectation of product of the entries of the matrix. If you have nice matrices, defined by groups or other objects like this, these are things that you have access to. We have combinatorial tools to compute. Discrete situation, this is often a matter of elementary combinatorics. In group theoretic situation, computing the expectation of words in random representations like I did over here is not a trivial matter. But there are many tools coming from representation theory that allow you to do this. There's something called blank calculus, which is extremely powerful. In the kind of models that I have in mind here, we have kind of powerful tools to at least compute formulas for these objects, even if we don't understand what these formulas mean. So that's the idea. We've replaced the norm by something that at least is computable. Whether we understand it is a different matter, but it's at least computable. And we have to choose p, the degree here, much larger than log n, then we expect to see the behavior of the norm. Does that make sense? And that's the basis of the trace method. And then typically, if you apply the vanilla trace method, which doesn't apply in these situations, but if you apply vanilla trace method in random matrix theory, usually once you arrive at this point, the problem boils down like this. You take the expectation of this, you write in a formula which is extremely complicated, and then you work very hard. Okay? So you have to do combinatorics of these. You have to understand the combinatorics of these equations to very good precision. And that's kind of the classical trace. Now, what are the problems with this method? Problems or difficulties? Let me write it. There are kind of two difficulties of a different nature. The first difficulty, I would say, maybe you could say it's practical. Okay? So it's typically easy, or at least doable, let me write easy, to understand the expected trace of x to 2p as the size of the matrix goes to infinity with p fixed. And so typically you have some kind of combinatorial expressions for this, right? They tend to be sums over combinatorial, some kind of expansion in combinatorial objects, like a sum over many graphs, right? But typically, if I fix p, the degree, and go to infinity, only the lowest order terms survive, and it's something you can understand relatively easily. Okay? So we have a very good understanding of these models when the dimension goes to infinity with the degree fixed. But that's not useful for the trace method, because in order for the trace method to work, you have to grow the degree at least much faster than logarithmically. And that's typically a much harder problem. When p grows with n, we get a kind of combinatorial explosion. Because what happens is that as we grow the size of the matrices, more and more terms in the expansion become non-negligible, and you have to control. Now, of course, we're mathematicians, so we're not scared by difficult questions, right? But it explains in some sense why doing these kind of computations tends to require a lot of hard analysis, right? In the combinatorial way. That's one difficulty. And the more complicated the model gets, of course, the more difficult this problem. But in the setting of random graphs, and this is, I think, the main reason, or one of the main reasons why even Friedman's original question took so long to resolve, there's a more serious problem, which is that it's not just hard, but it's impossible to make this method. So what is the reason that it's impossible? Well, remember that I drew this picture where I had outliers. There were some outliers in the spectrum. And these outliers happened at probability, which were polynomial in n, right? 1 over n to the power c for some m, for some constants m. So suppose that we know that xn is greater than, let's say, something strictly greater than 1. right? So something strictly greater than 1 with probability n to the minus n, let's say. This doesn't rule out that this converges to that as n goes to infinity, right? Because this probability is going to 0. But the probability is polynomial in n, so it's a rather large-ish small probability. It's a polynomial in n. So I claim that anytime you have outliers in the spectrum that have a polynomial probability, the trace method just fails. Why does it fail? Well, we can easily see it. Because you see, if I take the expectation of the trace of xn to the 2p, let's just lower bound this by just taking the indicator on this event, right? So on the event that this happens, this is greater or equal than 1 plus c to the 2p times x infinity to the 2p, right? On the event where this happens, what's inside the expression greater than that? And then you have to multiply that probability, which is n to the minus n. That makes sense? So if I divide both sides, if I do both sides to the power 1 over 2p, this 2p disappears, this 2p disappears, I will get over 2p. But this thing is 1 plus little o1 if p is much, much larger than log n, which is exactly the regime that we need in order to get the trace method to work. And so you see, actually, we get that the moments are actually bounded away from what we're hoping to get in the middle. So in very classical random matrix models like Gaussian models or random unitaries or things like this situation doesn't happen because you have concentration of measure, which tells you that rare events happen with exponentially small probability. And in those kind of situations, the trace method works very well. But random graphs are typical situations that are heavy-tailed, right? The distribution of the largest eigenvalue is extremely heavy-tailed. It has these outliers with polynomial small probability. And this is a fundamental obstruction to the success of the trace method. So what happens here is that the moments are completely dominated by the rare events. These rare events were called tangles by Friedman. Called this tangles in the graphs. Anytime, these rare events, they happen with probably going to 0, but not fast enough for the moment method. That's clear? And so as soon as you have heavy, moment method and heavy-tailed situations, they don't play well, right? So as soon as you have a heavy-tailed situation, the moment method breaks. And this creates huge complications. This is a very fundamental thing. It creates huge complications. And one of the reasons why these results about random graphs and about strong convergence of random permutations were so difficult is one has to somehow get rid of these tangles because they mess everything up. So they want to run a kind of trace method, sophisticated trace method, but it cannot work because of these tangles. So there is a whole machinery to try to condition on the absence of tangles. If you condition on the absence of tangles, then you can't compute the moments anymore because the distribution becomes nasty, right? So there is a whole set of ideas that are needed in order to get around these tangles, to eliminate these tangles from the problem so that you can then run some moment method on what is left. And then you have to still do the hard work, right? After that, right? So this kind of situations explain, in a sense, fundamentally why these problems are difficult and why these problems were considered difficult and why somehow one would expect one needs to do hard analysis. So far, so good? Yes.
So are these outliers coming from the self-loops or these are other outliers?
So there are many possible outliers. They don't just have to be self-looping. For example, if you have a complete graph of size, some size, it will also give you an outlier. The theorem that I showed you with that staircase shows that in this model, this permutation model of random regular graphs, it so happens that the self-loops are completely dominating all of the other events. They're completely explaining. So those are the dominant ones. But if you write down a very similar model to the one I wrote down that doesn't have self-loops, I can explain how to do this. Very, very similar models. You just replace the random permutation models by random matchings, basically. And then you will still get those tangles, but they will be different tangles. And what we expect is that you would still get this staircase picture, but the locations will be different, the events will be different, and we didn't do this analysis. Yeah, but in principle, nothing stands in our way of doing this analysis beyond being sufficiently good at group theory to run the argument. So does that make sense? But these tangles are very fundamental to these kind of models, and they really mess stuff up. So that makes this problem. So I'm now going to try to explain to you in a couple of stages what our method is doing. And the amazing thing about our method is that we don't care about these things. Okay? So we can do the analysis without worrying about the thing. We just ignore them. Okay? And the question is, how is this possible? So let me try to give you the most basic idea, and then I'll explain how we actually do it. So so the basis for our method are also moments, because these are the only things we can compute. Okay? And the kind of models I'm talking about, we don't know how to compute anything else. It's the only thing we have. So the basis for our method is that we start by computing the expected trace. I should say, I sometimes write trace with a capital letter and I sometimes write trace with a little letter. This means something slightly different. This is the normalized trace. So this is 1 over n times the big trace. The big trace is the one you're used to. At the level of resolution I'm talking about here, you can just ignore this. So the basis for our method is we're going to compute the expected trace of the H of these random matrices, where H is nothing else than a scalar polynomial of some degree, let's say Q. H is a real, not a non-computed, but just a real polynomial of some degree Q. So we're going to try to compute the expected traces of polynomials of these random matrices. Now, of course, this is nothing else than a linear combination of the expected trace of xn to the power p. Zero p between 0 q. It's a real polynomial, just linear combination of powers. Right? And these are the moments. I'm not doing anything here. I'm just saying the basis for our method is to compute the expected trace of polynomial. These are just linear combinations. Now we know that we're in trouble here, because we know, right, due to tangles, we know that these things are greater, let's say, than something exponential in the degree times the object that we care about. So we know that there is a multiplicative factor that's exponential in degree where these are bad. And now we just take linear combinations of these things, right? So we hope that the expected trace of h of xn is close to the expectation of the trace of x infinity. But it seems hopeless because, it's just a linear combination of moments. And we know the moments are already an exponential factor away from the limiting object, right? So it's not clear what we have gained.
So is it clear that if you use a different basis for polynomials, you will still face this law?
So I think what I'm going to say is better than what you're saying.
Now Q is fixed and n goes to infinity.
So, but we are going to get quantitative results. So, at the end of the day, we have, and one of the miracles is that we are going to be able to get quantitative results for free, but we will see that. But for now, I just want to focus on what is, not yet on the method itself, but why does it work? So it seems we're already in trouble. There's nothing gained here. But, for example, we can prove, what I'm writing now is not enough to prove strong convergence, but it already showcases the phenomena I want to explain. We can prove that if I take the expected trace of h of xn, and I subtract the same thing with infinity, the infinite object is not random, so I just write the trace. Whatever that means, you can take my word for it exists on the C-star algebra. We can prove bounds that look like this. In this case, we get maybe the 4 over n times the L infinity norm of h. on the interval minus kk, where k, remembers, is a priori bound in the norm of the matrix. And you notice that this bound is polynomial in the degree. Now, we just said that each term in this H monomial is a multiplicative exponential factor away from what it should be.
This is for some carefully chosen, like.
No, this is true for every H, every polynomial H.
But you
Of degree Q.
you would want H where for which the infinity norm is smaller, right?
Exactly. So let's do a thought experiment. What happens? I claim it's true for every polynomial. So what happens if I take h of x is x to the q, right? Then I get back a monomial. This bound is still true, right? So I get the difference is bounded by something polynomial in q. But what is the L infinity norm of x to the q over minus kk? It's k to the q, which is exponential in q. And I get absolutely nothing, right? Nothing interesting. So this doesn't contradict what is going on. But of course, what I have here is the L infinity norm of H. So instead of working with the moments, I can take a polynomial that is actually bounded in the interval minus kk. Now, if I want the polynomial to be nicely bounded in the interval minus kk and still have large coefficients, I can't take a sum of monomials. I have to have cancellation, right? I have to take, right? What will have to happen? Monomials try to grow exponentially, right? So if I want to cancel this exponential growth, I have to have polynomials where I have positive and negative coefficients, where I have cancellation, right? And what this theorem is saying is that if I take such a polynomial with cancellation, then suddenly this exponential error that I get from the monomial has canceled, and I get polynomial dependence on Q. Which means, in a sense, that you see each monomial is completely dominated by the tangles. But if I take a bounded polynomial, and I take the linear combinations, it seems that the effect of the tangles basically cancels between the monomials, and they're gone. And we don't suffer from them. So the method captures cancellation. And now you can imagine why this is very difficult to accomplish by combinatorial means, right? Because when you do combinatorics, right, you have combinatorial expressions. At the end of the day, you're counting terms, right? The combinatorial methods are not good at capturing cancellation. But somehow or other, we have to capture this cancellation, and we don't really have a hope of doing that by combinatorial.
Do you think you would be able to learn something similarly useful just by considering the difference of two monomials?
No. Because again, you can't really generate much cancellation. In fact, our method has two parts. First of all, how do you prove such a thing that witnesses the cancellation? The second part is, how do you apply such bounds efficiently to maximize the effect of the cancellation? And in fact, we will always, I don't know if, we'll see. We will always apply these bounds to polynomials which have maximal cancellation, which are the Chebyshev polynomials. So in order to exploit this, right, first we have to understand how to prove such inequality. Then in order to exploit them efficiently, we actually have to maximize the cancellation that we get out of our bounds. So we will never apply them in a situation like this. That's the second step. Are there any questions?
So just to understand the difficulty, Ramon, the issue now would be that there is not a combinatorial way to understand the Chebyshev moments.
No, I don't know how to prove it. There is a confusion here which you would only be confused by if you knew the previous works on the topic. The Chebyshev polynomials actually also appear in Friedman's paper. There is if you have a d-regular graph and you take the Chebyshev polynomials, rescale to the interval minus 2 square root d minus 1 to 2 square root d minus 1, which is the interval where the limit lies. If you take the expected trace of such a Chebyshev polynomial of the adjacency matrix, this is actually a combinatorial object. It counts the number of non-backtracking paths in the graph. This is something that Friedman uses very heavily, and Bordenave and Collins use a different way of using it. So there's a very deep connection between Chebyshev polynomials and combinatorics. It turns out that
That's for any irregular graph.
for any d-regular graph, if I take the Chebyshev polynomials rescaled to the interval minus 2 square root d minus 1 to 2 square root d minus 1, take the expected trace. I have to admit, I don't remember the exact statement. There's Chebyshev polynomials of the first kind and the second kind, and you have to take it correct. But this counts the number, so it's actually, it turns out that this will count the number of non-backtracking walks in the closed walks in the graph. And then that helps you a lot doing the combinatorics. It's much simpler to count non-backtracking walks than. However, this has absolutely, so the reason this is so confusing is because this has zero to do with what we do. Because our Chebyshev polynomials we're going to use are rescaled to the interval minus kk. That is a completely different story. So they just superficially look the same, but these things have nothing to do with each other.
Which is minus dd.
Yes, minus dd, not minus 2 squared d minus 1 2 squared d. So something really completely different is going on here. Just if you have read the previous papers and you saw the word Chebyshev here, you might think that these things are related. They're really completely disconnected. So here we're really doing something else. We're using Chebyshev polynomial to achieve analytic goals, not to achieve combinatorial goals. Good. So I think in some sense, I haven't explained to you how we achieve this, but at some level, I believe that this is one of the main secrets of the method, that we are able to capture this cancellation, which I really had I would never have conjectured something like this. It's something that came out from the method. I would never have conjectured that something like this. But once you have this kind of cancellation, the tangles are not in your way anymore. And it explains both why the method is easy to apply, because you don't have to worry about all of these complicated things happening. And at the same time, it explains why we get strong. So let me try to explain one of the main kind of ideas of how we achieve this cancellation. So we don't know how to do this combinatorially, so we need some other method of achieving this cancellation. And then if I have time, I will try to show how we put this together with, once you have these kind of estimates, you still need to extract statements about the norm, and there is a kind of machinery. So let me start by explaining what we use as input for this thing. So we use two things as input for this method, which we have in all of the models that I've described so far. So these are and we are using these properties. These are kind of soft properties, and we're using them in very helpful. The first thing that turns out to happen here, if I take the expectation of the trace, h of x. So what I said is the reason that we want to work with polynomials or with moments is because in the kind of models we're talking about, discrete models, group theoretic models, we have tools to compute these things, right? To write formulas for them. It turns out these formulas, we cannot just compute them, but they're actually very nice formulas. It turns out that these objects will become rational functions of the dimension. This is something we see. So the rational function depends on which polynomial I take. And I can write them as rational functions of 1 over n. So this is nothing else but some polynomial of 1 over n. So this one depends on h. And will be some denominator. Typically, the denominator doesn't depend on h, it only depends on the degree of the polynomial. But these are formulas that you get when you compute.
Sorry, what's our model? I see it, but.
Random permutation matrices, random representations of unitary groups, random representation of orthogonal, Gaussian random matrices. Okay, in the case of Gaussian random matrices, these are even polynomials. You don't have them.
So you have to compute these.
You have nice symmetric models, and typically when you have models that are invariant under some large symmetry groups, you get it, not always, but in all the situations I've described, you get this behavior. So for Gaussian models, these are typically called genus expansions. These are polynomials. For non-Gaussian models, the rationality of these functions comes from Weingarten calculus. It comes from representation. And so it's a fact that we have. Now, of course, these rational functions are very complicated, right? I told you I can compute them. Doesn't mean I understand what these rational functions do. The rational functions are very complicated. They have horrendous, like absolutely horrendous formulas. And, typically the fact that these things are rational is considered to be useless. Yeah, you have a rational function, but so what? It's like some awful rational function. I don't know how it behaves. Then I have to work right? I have to try to understand how it behaves. But there's some easy things, because what typically happens here is that the degree of FH and the degree of the denominator is proportional to the degree of the polynomial H. And so they are rational functions, they have some nice degree, right? It's proportional to, for us, polynomial in view would be enough, but typically even linear. But they're very complicated, right? So this in itself is a purely qualitative property of these functions. It's not something quantitative that we can compute, just qualitative. The other thing that we know about these functions is what I wrote over here, is that typically these functions are very easy to, if I fix P and I let n go to infinity, these functions are very easy to understand. And or very easy, they're relatively easy to understand, you know, because only the lowest order terms of these functions show up and we can understand those concepts. But typically what we have is we have some kind of expansion. So for example, I typically write u0 of h plus u1 of h over n plus, let's say, O of 1 over n. I can go to higher order if I want. I can take this to any order. Go up to order 3, then I have it mu3 over n to the 3 plus O 1 over n. And these news, they're just linear functions of h, right? Because this side is linear. And typically these news, at least for the lowest order, are something that we can understand fairly easily using just my inspection, basically. Okay, so, but these are asymptotics as n goes to infinity with h being fixed. But typically that doesn't tell us much about, or much if anything about the loop. Typically, if we want to say something about the outliers, right, we would need to understand this expansion up to an order which grows within. Right? That's classically what we see in the moment method, and that's what's used in basically most previous, not all. But here I'm not saying anything about how this remainder term depends on n. I'm just looking at the n goes to infinity asymptotic. So this is also very soft kind of information that we have about these functions. This is not this is not the kind of quantitative information that would be needed to run, for example, a trace. This is it. This is our input. So we have one kind of soft qualitative property of this function, just that it's rational and we have some unknown degrees. Doesn't tell me anything quantitative. And we have one property which says something about the large n asymptotics, right? But just the lowest order behavior of this function. There's no control of the error term. Now, what is the main? All of the steps in the proof are important, but kind of the most surprising part of the proof is what I'm going to describe now, which is what is allowing us to prove estimates like I have over there. And this is really where the cancellation comes. So what we're going to do is, my claim is that just from this information, so we have just n goes to infinity asymptotics to the lowest order, and we know it's rational. We can prove a very strong quantitative version of this expansion with a very strong error term over here. We get it for free. So we start with asymptotic information and we get non-asymptotic information for free. Okay? How do we do this? Here's the idea. So what do we want to do? I want to bound the expansion. By the way, notice that mu0 of h, that's just the limit as n goes to infinity of this. That's just the trace of h of x infinity, right? That's what we care about. This mu1 is something else that we typically understand very well for low degree polynomials. I will come off. So what I want to do is I want to upgrade this asymptotic expansion to a quantitative state. So I want to bound the expected trace of x, and minus mu0 of h, minus u1 of h. I want to bound. So what is this quantity? Well, remember, this is just a rational function of 1 over n. What is u0 of h? That's just the limit as n goes to infinity of this. If I let n go to infinity here, then just phi h is 0. What is this term? I take phi h of 1 over n minus phi h of 0. I divide by 1 over n, and let n go to infinity. Well, mu 1 of h is nothing else than the derivative of the function phi h at 0. Now this will look very familiar because that's just a Taylor expansion of the function phi at 0. Right? I just applied Taylor's theorem. This is bounded by what? 1 over n squared times what? I take the second derivative of phi h, and I have to take it uniformly at least in the interval 0, 1 over. There it is. Wonderful, right? I just applied Taylor's theorem. Don't worry, I have it. Okay? Now, this seems completely worthless because what do I know about this function phi h? Well, I happen to know that at the points 1 over n, this function corresponds to the random matrix that I started with. But I can't apply Taylor's theorem on a discrete grid, right? I mean, to apply Taylor's theorem, I need to bound the derivative everywhere. So I need to understand how this rational function behaves at points that are not of the form 1 over n. Now, it would be wonderful if we, for example, could speak about random matrices dimension 7.5, but there is no such thing. So in a sense, what I've done here seems, obvious on the one hand. On the other hand, it seems completely worthless because we know nothing about this function. This function has no interpretation off of the grid. Right? So we completely lose the spectral interpretation of this function. It's just some rational function and we don't know anything. So, this seems like a completely worthless idea. The observation is that these are not just any functions, they're rational functions. Right? So in principle, right, if I had a continuous function on a grid, it can behave kind of arbitrarily off the grid. Right? It can oscillate, right? On the grid points, it can be very small, and then off the grid, it can oscillate like crazy. But these are rational functions of bounded degree. And rational functions of bounded degree, they cannot oscillate like crazy off of the grid. Right? They are very restricted in the way that they can oscillate. And in particular, the ways in which they are restricted was understood very long ago. And there are two key facts. One of them is the inequality of the two brothers Markov. So I'm going to write these inequalities for polynomials f. But in fact, we just applied these inequalities to the numerator and denominator of this rational function. So just write them for polynomials. If f is a polynomial of degree, this means this is the set of real polynomials of degree q. Then if I bound the derivative of f on the interval -1, 1, it's always bounded by q squared, the degree squared, times the size of f on the interval -1. So unlike general functions, the derivatives of polynomials cannot be arbitrarily large. If I have a bounded degree polynomial, its derivative cannot be much larger than its largest set. Does that make sense? But this is it's a non-trivial inequality. It's a very classical inequality in the geometry of polynomials. And
Tied for Chebyshev, right?
I beg your pardon?
This is tied for Chebyshev.
And this is equality for Chebyshev polynomials, scaled to the -1. These are the polynomials that have the largest cancellation. And already here you see the cancellation because we're talking about the L infinity norm. Of course, if I take here x to the, something like 2x to the cube, I get here something exponential in cube. So it's the fact that they're bounded that gives you the cancellation. Now, what this allows us to do is to say we have to bound, we have to bound the second derivative. Of course, you can iterate this twice. The second derivative of f is bounded by q to the 4 times the infinity norm, right? Okay. So what this allows us to do is say, okay, if we want to bound the derivatives of a function, we might as well just bound the function itself. And what we now want to say is, well, actually define, okay, we don't know anything about the derivative of the function, but the function itself we understand very well because of the trace of h. Obviously, it's bounded by the L infinity norm of h, right? Just by spectral theory. The only problem is that's only true on the points 1 over n. But we still have to deal with the fact we go off of 1 over n.
Are we looking at constant degree Chebyshev polynomials now, or do we have to look at?
I'm dealing with a fixed polynomial of degree q. H is a fixed polynomial of degree q. We're going to get quantitative bounds. When we have quantitative bounds, then of course we can play with the parameters however we want. Okay? So the nice thing here is that you see The nice thing here is that if a function cannot move too fast, then it can also not move, if it's bounded on a grid, it also cannot move too far away if you go off the grid. Right? And it's actually a corollary of the Markov inequality. It's a kind of class corollary. I believe it's due to Rivlin and Cheney from the 1960s. Don't quote me on that. It wasn't being recorded. But, which says that if I take the L infinity norm, here I've rescaled things to -1, 1. Of course, we will play with these scalings, and that's just a matter of the chain. So if I take a polynomial uniform bound on the interval -1, 1, it's actually bounded by a constant. I think you can pick two, but you can play with the constant, but a universal constant times the maximum of the polynomial on a discrete set. Think of this as a discrete set, like the grid 1/n. As long as for I, where the spacing between the grid points is 1/q squared. If I take a polynomial of degree q, and I sample it on a grid of degree 1/, if I sample it on a grid where the spacing between the grid points is at most some constant over q squared, then basically the maximum of the polynomial everywhere can be no larger than the maximum polynomial. So this is the resolution on which you have to.
You don't care about q squared, right? So any power of q would be.
For us, to prove strong convergence in the simplest way, we don't care. We just need things to be polynomial in q. But if we want to push quantitative results, then we do care about the power. And for example, if we could replace this q squared by q to the 3/2 here, then we would have proved n to the -2/3 fluctuations, Tracy-Whittem scale. So we do care very much about these powers. And in fact, we have better tools now than the tools, at least in the second tool I'm writing down here. This is in a forthcoming paper that allows us to get better rates and things like this. But for the basic story here, you should not worry about the precise constant. You should just think about this as anything polynomial. Once you have the basic methods, you want to push it, to squeeze it, to get the best possible quantitative results, because that will allow you to grow all the parameters the fastest. So we do care about it.
So this is the same, this corollary is the same fact used by Nissan and Szegedi law bound for.
So the story behind this is that in theoretical computer science, there is a kind of classical method of Nissan and Szegedi. Are they the original ones?
Yeah.
Yeah. Who used, I'm not an expert, but they use exactly the same idea to prove complexity lower bounds for certain problems in theoretical computer science. So they're talking about functions on the discrete Q. Again, it's a discrete model. You have a function, a symmetric function on the discrete Q. So you can think of this as a function that's just a function of the number of ones, right, in the string of bits. So you think of that as a real polynomial, right? But you only know something about the polynomial, the value 0, 1, 2, 3 until n. Okay? And then to prove complexity lower bounds, they say, well, let's forget about the fact that it's only defined in 0, 1, 2, 3 until n, because it's a polynomial. We have a bound on the degree. So we can apply these two lemmas and just bound it everywhere. And now we have a tool in order to prove complexity lower bound. How exactly they do that and what they prove, I don't know. I think it would be better to ask. Anthony Chen, one of my co-authors, he was a graduate student at Caltech at the time that we did this work, and his expertise in quantum information theory, where these kind of techniques are used. And he came up with the idea that maybe this is brilliant idea that maybe this is applicable to random matrices, and actually making it work so well that you can achieve strong convergence required additional ideas. But for us, I don't know anything about complexity theory. For us, this was completely out of the blue. I never thought about such a method. Never seen such a method in random matrices. But it works like a charm, you see, because once you have these two tools, you can just, now it becomes an exercise. You can go home, you have to apply the chain rule, so you can apply this to both the numerator and the denominator. But other than that, it just becomes an exercise. You plug it in here. And eventually, what will you get? Well, if you do it the way I wrote here, you'll get q to the 8 divided by n squared times the L infinity norm of h on minus q. That's all we have. We use nothing here. We just use this irrational function. We have a bounding. This 8 comes from two places. It comes from the fact that I get q to the 4 from having two derivatives. And that I have to, right, the spacing of the grid 1/n is very large near the endpoint, right? It's of order 1, from 1 to 1/2. I need the grid spacing to be less than 1/q squared. So I need to restrict myself to n sufficiently large that the spacing between the 1/n's is of the right. That's where the other q's come. So this is where the cancellation comes. And again, without having these kind of tools coming from the theory of polynomials, it seems kind of very hard to imagine how you would access it. I have 1 minute, I think. Do I have 1 minute? Let me just very, very briefly, once you have these estimates, which are really at the core of the method, the difficulty becomes how do you use them efficiently? And what we want to do is, even if we were to start with a polynomial of degree q, it's typically not efficient to apply this method where h is the polynomial itself, because you want to maximize the amount of cancellation. So what you will do is you will take your original polynomial and expand it in terms of Chebyshev polynomials. The Chebyshev polynomials are the ones that make this equality. So these are the best polynomials. When you take your original polynomial, you expand in terms of Chebyshev polynomials, and what you will get here, rather than getting the degree to the power 8, you will get the sum over k of ak, the coefficient of the k Chebyshev polynomial, times k to the 8. And this will give you a smoothness. So let me just write by Fourier analysis. You can upgrade this inequality just by basic Fourier analysis implies the self-improvement. Where rather than having here something that depends on the degree, you get here a smoothness. It's the uniform norm of the function, and it's 9 first derivatives. Just by Fourier analysis allows you to upgrade that to this. And now you see the degree has disappeared. Now, this is true for every polynomial, it's true for every smooth function. You just take the limit and apply this to smooth function. And then the idea of the method is that we will fix test functions that look like this. If you have here x infinity minus x infinity, and here you have x infinity, you take a smooth test function that's 0 over here, and that becomes 1 outside an interval. This will be x infinity plus epsilon. Here you have minus x infinity minus epsilon. You will take these kind of smooth test functions that approximate indicator functions. And because of this machinery, we can now directly apply that in the situation. And you can imagine the expected trace of this is just counting the number of eigenvalues that are greater than x infinity plus x. And there is a last issue in the method, which is to try to control these error terms. And let me not go there, but it's explained in the paper. It's also something we can do very easily using moments. That doesn't require really much quantitative input besides very basic content. So I hope I've given you a flavor of how the method works and why it works, at least why I think it works. And exactly how far it goes, we don't know yet. So we're hoping to push it further and see what happens. Thank you.
It's been a truly wonderful talk. Any more questions?
Is it easy to see what the obstruction is in getting Tracy Wyndham?
From our perspective,
From your perspective.
Okay, you're two separate questions. There's Tracy Wyndham itself. This is completely outside.
Something about the scale of fluctuation.
Let's just talk about n to the minus 2/3 scale fluctuation. Let me answer your question not in the setting of random permutation. In the setting of random permutations, there's another difficulty which is very easy to explain. I'll mention in a moment. But for example, let's just go to polynomials of GU. Even if you take polynomials of Gaussian random matrices. For Gaussian random matrices, we know Tracy Wyndham. It's a computation. But even for arbitrary polynomials, it's expected that in any polynomial of Gaussian random matrices should have fluctuations of order of most n to the minus 2/3. That's open. This is normal. Very little is known about the behavior of polynomials of random matrices at this level. What stands in our way there is exactly the power here in the Markov inequality. It turns out that the polynomials that show up, so in the case of GUE, this rational function is actually a polynomial, something very easy to see. And it turned out these polynomials are kind of not the worst case polynomials. They behave slightly better than the worst case polynomials. And one needs a kind of, if one can improve, I think, by a square root q or something like that, the Markov inequality or the Bernstein inequality, one would get n to the minus 2. In that situation, we reach n to the minus 1/2. We are just 1/2 of a power off. And the problem is that we simply do not know how to achieve this, right? We know that that's where the obstruction is. But you see, this is a general tool that applies to any polynomial. What kind of, is there a qualitative property of the polynomials that show up here that we could exploit to get better inequalities? There are old results, for example, of Paul Erdős about improvements to the Markov inequality in situations where you know something about the roots of that there are no roots inside the unit disk. Unfortunately, I did some numerical computations and I found roots inside the unit disk for these polynomials, so it's not applicable. So yeah, we know exactly where the obstruction lies, but we do not know at the moment kind of how do we, whether is a kind of qualitative method to figure out. In the case of random permutations, if you wanted to achieve even n to the 1/2, which we're getting for GUE, you would have to get rid of the thing. So the tangles are restricting us to a certain level. I think right now we're down to n to the minus 1/6. But if you wanted to go all the way to the n to the minus 1/2, you would have to get rid of it. And that means you would have to somehow combine the method that we have here with some of the techniques developed by Friedman and by Bordenave and Collins to remove tangles. It seems plausible that this is possible, but I haven't been very motivated.
Okay, the interest again, let's take that.